into it, right? So B2, number one voted thing to go through, right? So this right here is a bit of a, I would say, challenging problem in that it makes you think about two different concepts in a way that isn't directly, I think, discussed in the lecture. And you don't, necessarily think of it directly there, but it's a good problem solving problem, right? Because you can work your way through it, right? If you just take a moment and think about it, right? So what the question was is, how does the bond energy of H2O gas differ from the standard enthalpy of formation of H2O gas, right? And so if what we're looking at in these cases, right, we can look at the end of the packets, and so what we can see is that, right, the bond energy of, an OH bond is equal to 463 kilojoules per mole, right? In that case, right? And so that's what the bond energy is of one OH bond, right? And so H2O, it has two of those. And so, overall, right, the bond energy that you would expect to have stored in the bonds of H2O is going to be double that. So, right, so that's 463 times 2. So that comes out to 926 kilojoules per mole, right? So that's how much energy is stored in those bonds. If we look at the end of the packet, right, and we look at the delta H of formation for H2O gas, what we'll see is that value is, let me just look at it real quick. H2O gas is negative 242 kilojoules per mole, right? So those are two very different values, right? One is negative, one is positive. One is 242 kilojoules per mole, right? The other one's 926 kilojoules per mole. So if you're looking at that, right, you're like, there has to be some kind of disconnect. Something is wrong. Something is off there. But you have to think about what it is that you're actually talking about when you're talking about either bond energies or delta H's of formation, right? And so when we're talking about bond energies, what we're talking about is the energy that's stored in a bond. And the way that we use bond energies in thermochemistry, right, is that we know how much bond energy stored in a bond. And so either that's the amount of energy that we have to put into the system for that bond to form, or that's the amount of energy that gets released when those bonds are broken, right? And so it's all strictly bond centric. Whereas in the case of delta H of formation, what we're looking at, right, is the formation of molecule, right, in terms of comparison to the elemental forms in those cases, and that in those cases right there, right, that's what that molecule is in terms of what the energetic state it is. Whereas in the case of the bond energy, right, that's the bond energy that's stored. That doesn't take into account anything else. And the only way that you can really relate that to delta H, right, and to enthalpy, which is what you have for delta HF, right, that's the enthalpy of formation, is you have to take it into account with how other bonds that are either formed or broken to then make H2O, right? And so there's two different equations that I gave at the beginning of the packet, right? So you have, let me just pull both of them up real quick, right? So you have, did I not include them here? Oh yeah, I did, right there, right? So you have two different equations, right? So there's the delta H of reaction, right, where you have, right, the bond energies, right? So we'll just refer to that as D, right, of the bonds that are broken, minus the bond energies of the bonds that are formed, right? And so that's how you get delta H reaction using bond energies. Whereas in the case of using the Hess's law, right, the way that you can approach that then is you have delta H of reaction, where you then have the delta H of formation, right, of the products minus the delta H of formation of the reactants in these cases, right? So those are two different but slightly similar equations in these cases. And so if we're looking at this right here, right, ultimately what we have to then consider is, to get from the bond energies to the delta H of reaction, right, that would then be, the delta H of formation. So to say, we'd have to include what goes on with the HH bonds and what goes on with the OO bonds, right, because those are going to have to get broken to form the new OH bonds in those scenarios, right? And so that's where the difference comes from those two cases right there. But we can show how you can actually use the standard enthalpy of formation of H2O, right, to get the OH bond energies in these cases, right? So taking a step back, right? Let's look at what the, reaction is for the formation of H2O, right, from the elements. So in the case of the delta HF, right, delta HF formation for H2O, right, the reaction that we have is we have H2 gas, right, that's the elemental form of hydrogen, plus O2 gas, right, that's the elemental standard state form of oxygen, right? Those two react together in some shape or form, right, to form H2O gas. Now we can just simply balance this. And so typically you don't use half coefficients, right, in a reaction, but in the case of like delta HF formation, right, you're always, everything that you're given is always to form 1 mole of whatever that product is. That's what that relationship is, and where those values are tabulated. So you have to then, in those cases, right, you're going to use half a mole of O2 gas in that case, right? But whereas if, it was a normal reaction, you wouldn't have them that way, right? You would always want to have full integer coefficients, just as a note, right? But in the case of delta HF formation, that's fine, right? Because everything is referenced to just simply forming 1 mole of that product, right? And so this is the jump back, right? So we're at delta H of formation of H2O here, right? So that's what that reaction is in this case. And so that's negative 242 kilojoules per mole. Now, one thing to think about, going back to bond energies, right, is that when we're talking about bonds breaking, right, we're talking about what's referred to as homolytic cleavage, right? And so homolytic cleavage means that you break the bond and each atom takes away its electrons that it started off with, right? So in the case of OH, right, an OH bond, the hydrogen takes its electron, right? And so it then has a 1 electron species. The oxygen then takes its 1 electron that was part of that bond, and it forms its species. And so, if we were to write out what that reaction of OH breaking apart, right, and releasing all of that energy is, it would be, ultimately, right, that you have 2 OH bonds, in this case, would break apart, and you would form then, right, 2 H dot, atoms, and then 1 O dot dot atom, right? So 1 oxygen that has 2 unpaired electrons, and then, 2 hydrogen atoms that have 1 unpaired electron. And so, sorry, I got a message real quick that I need to right, so that's what you have in this case, in terms of the bond breaking reaction. And so we can look at the back of the table, right, and we can see what the enthalpy of formation is for H dot, right, which would just simply be, H gas on its own, right, no H2 or anything like that. And same thing with O dot, or O dot dot, right, and so that would be, O gas, right, again, just on its own. And so, both of those values are tabulated in the back. And so if we write out what those reactions look like, right, what we have in this case is 1/2 H2 gas, right, is going to form H dot gas in this case, right? And so that has a delta H of formation of, what is it? 217 kilojoules per mole, right? And so then same thing, if we go into oxygen, right? So that's going to be then 1/2 molecule of O2 gas, and that's going to then form O dot gas in this case, right? That's delta HF. And so that will be a value of, where is it? 249 kilojoules per mole, right? Right, so those are all the delta HF values that we have in these cases right here, right? And so, and ultimately, right, what we're looking at in this reaction is just simply the amount of energy that you would release, right? The delta H of the reaction where, the different, H2O essentially splits apart, right? The reaction that we're looking at, right, that I have written right here, but if I were to write it in, I guess, like a more formalized way, right, it would just simply be H2O gas. goes and it forms H dot gas plus, or 2 H dot gas, sorry, plus 2 H dot gas in this case, right? So you have all of that right there to break all of those apart and figure out like how much energy is either going to be stored or released in those cases, right? For this delta H reaction right here, we have that, right? So now all we have to do is we can just use now this formula that we have right here, right? Where we have the delta HF, or the delta HF formation of the products, right? The sum of all of those minus the delta H a formation of the reactants, right? And so all of those should add up together in those cases. And so if we do that, right, what we get then is taking, right, we'll have to have two equivalents of the, delta HF of H dot gas, right? Because there's two of them that are being formed. So we have 2 times 217 kilojoules per mole plus, right, the oxygen reaction, right, to form the O dot dot, right? So that's 249 kilojoules per mole. Those together minus, and so then now, right, we just simply have the reaction where we're formed, right, the delta HF of H2O gas, right? So that's negative 242 kilojoules per mole in this case right here. So if we take all of that and we plug it in, right, 2 times 217 plus 249 minus negative 242, right, what we get is 925 kilojoules per mole, right? That's how much energy has to be put in, essentially, to convert H2O into its individual components in those cases, right? That's how much energy is going to be stored in that scenario, and that matches, right, pretty closely what we have up here, right, for the bond energy of H2O, right? So if we were even to just simply take this, divide it by 2, right, so that we get each individual O2 or OH bond, right, we divide that by 2, what we get is 462.5 kilojoules per mole, right? And that matches, what we have in this case, right? That's how much energy is then stored in the bonds, right? So 462.5, right? We're 0.5 kilojoules per mole off from, the value that's in the table, right? And the value that's in the table is just simply a standard energy, an average energy, right? And so, but we got pretty close, right? Just using delta H of formation values to work our way using like Hess's law and our understanding of bonding to get to the point where, we're able to figure out what the bond energy is of a system, right? Just by using delta HF values that we have. And so that's a pretty, I think, powerful tool in that case. So, but yeah, so that's how you do B2.